All right, let's talk about intermolecular forces. And before we get into intermolecular forces, let's make sure we understand the difference between the two main types of attractive forces. First of all, intermolecular forces, which is what we're going to focus on mostly in this chapter, are the forces of attraction between molecules. And so there's four types that we're going to be concerned with in this class: ion dipole, hydrogen bonds, dipole-dipole interactions, and London dispersion forces. An intramolecular force, if you imagine if somebody said, I'm traveling intranationally, all that would mean is they're traveling inside a country. I'm going from Kansas to Missouri. I'm traveling intranationally, right? So the attractive forces within a molecule, like covalent bonds, okay, that would be an intramolecular force. Or if you have an ionic compound, for example, ionic bonds, those would be intramolecular forces. But again, we're going to talk a lot about intermolecular forces in this chapter because the forces between molecules are going to govern things like melting points and boiling points. So if we go over to the table here, you see that the intramolecular forces, ionic bonds and covalent bonds, are much stronger than intermolecular forces. So ionic bonds are the strongest of all, followed by covalent bonds. But then if we look at our intermolecular forces, ion dipole interactions, hydrogen bonds, dipole-dipole interactions, and London forces, you can see, again, not only are they weaker, but you should know the order. You should know the ion dipole is the strongest, followed by hydrogen bonds, then dipole-dipole, and then London dispersion forces are the weakest of all of the intermolecular forces. So let's cover them one by one, and we're going to start out with the strongest of the four intermolecular forces, and that is the ion dipole interaction. And the ion dipole interaction is what you might guess it is. It's the attraction between a charged ion and a polar molecule, right? Because we know that a polar molecule is going to possess a dipole, right? So if we have something like water, water is a polar compound, right? It's a polar molecule. It has a dipole in it. Well, why is it that water can dissolve sodium chloride, which is an ionic compound? It's because of the ion dipole interaction between the ions, a sodium cation or a chloride anion, and water. So first you see the positive charge of sodium can align with all of the delta negatives on the oxygens in water. So what these ball and or these sphere diagrams here, these are supposed to be water molecules here, right? And you remember in water, if I draw a water molecule bent like this, you remember that the oxygen is, that's not a very good delta, that the oxygen is delta negative, but the hydrogens are delta positive. Also, I should include the lone pairs in there. So the way water is going to work is that it's going to align itself so that the delta negative of the water molecule is going to interact with the delta positive of the sodium and help to dissolve it. Well, the cool thing about water is that it has two faces, right? It has the delta negative face where the oxygen is, but it also has the delta positive face where the two hydrogens are. And so in order to dissolve the chloride ion, Cl minus, what it's going to do is you see how all the water molecules here are flipped around compared to the ones that are dissolving the sodium cation. And so the delta positive of the hydrogen of these water molecules is interacting with the I shouldn't say delta, the negative charge on the chloride ion. And so that's an ion dipole interaction. Next, we move on to hydrogen bonding, and hydrogen bonding is the reason why water has such a high boiling point. I mean, we take it for granted that water has a boiling point of 212 degrees Fahrenheit or 100 degrees Celsius, but it's because of hydrogen bonding. Okay, and hydrogen bonding is the attraction between a hydrogen atom that is bound to either fluorine, nitrogen, or oxygen in any fluorine, nitrogen, or oxygen atom on another molecule or a distant region of the same molecule. So the way you can remember this is that in order to have hydrogen bonding, you have to have FON, F-O-N. So you have to have a hydrogen bound to fluorine, or a hydrogen bound to oxygen, or a hydrogen bound to nitrogen. If you don't have one of these, you cannot have hydrogen bonding. And so if we look at the example that's shown here, they're showing you the hydrogen bonding that takes place between water molecules. So if I put my delta positives here by my hydrogens, my delta negative over here, and my lone pairs like this, you can see that what they're showing here is sorry, I put this delta negative here, but they're saying this delta negative is tied to the lone pairs on the oxygen. So what they're showing here is the interaction between the delta negative on the oxygen and the delta plus on a hydrogen. And you see another one here, and another one here, and another one here. And so that is hydrogen bonding. And hydrogen bonding is nothing more than a dipole-dipole force that we're going to review on the next slide. It's just a very strong type of dipole-dipole. So it's just a very strong dipole dipole force. Okay, that's all it is. It's just in a class of its own, and we call it hydrogen bonding. In order for you to understand things like the double helix in DNA or an alpha helix in a peptide, you have to understand hydrogen bonding. So hydrogen bonding is crucial when we get to biochem. Next, we have a dipole-dipole interaction. And a dipole-dipole interaction is just an electrostatic attraction between two polar molecules, so ones that have permanent dipoles in them. So if you take a look at hydrogen fluoride, right, this is, if I just draw a simple Lewis structure of HF like this, you will remember that fluorine is the most electronegative element in the periodic table. And so it's going to be delta minus, which is going to make the hydrogen delta plus. And so you can see that if two HF molecules are going to interact with each other, that the delta minus of the fluorine on one of them is going to interact with the delta positive of the hydrogen on another, and vice versa. So we have a dipole-dipole force of attraction here, and we have a dipole-dipole force of attraction here. You can also see end to end here between these two molecules where the delta negative of this fluorine is attached to the delta positive of this hydrogen. So again, whenever you have two molecules that have dipole moments, the delta negatives and the delta positives, as well as the delta positives and the delta negatives, if that makes sense, they are going to be attracted to each other. And that's another kind of dipole, intermolecular force. And so again, if we go back to the previous slide, again, hopefully this clears it up, that all that hydrogen bonding is, it's nothing more than a dipole-dipole force, but it's just a very strong one when you have FON, right? When you have a fluorine bound to hydrogen, or an oxygen bound to hydrogen, or a nitrogen bound to hydrogen. And the weakest of all the intermolecular forces are the London dispersion forces. Just remember, even if you have a molecule that's completely nonpolar, um, every molecules experience London dispersion forces. So if anybody ever asks you, are there London dispersion forces between these two molecules? Any two molecules, there always will be. They're always present, but they're very weak. Okay, they are the weakest of the attractive forces acting between particles of all matter. They result from momentary non-symmetric, this should be unsymmetric, but anyhow, I'm nitpicking here, unsymmetric electron distributions in molecules or atoms. In fact, there's a little blurb in the textbook about geckos and how they're able to climb, a vertical wall, or they're able to walk on the ceiling or something. And that's partially due to London dispersion forces. So let's say you have two helium atoms, okay? Nothing fancy, just imagine this is a helium atom and this is a helium atom. Well, if they're two helium atoms, they have the exact same um, electronegativity, they have the same ionization energy and all that kind of stuff. But if you can imagine the two electrons, right, because helium is just one s2, if you imagine the two electrons outside of the nucleus are perfectly spaced apart or something like this, and these two are perfectly spaced apart, right? There's no dipole in any of these, all the charges are balanced out. But what if, in just a moment of time, both of the electrons end up on one side of the helium atom? Because remember, electrons are in constant motion, okay? If you don't remember me saying that, I'll put it to you another way. One of my friends describes it. He always says electrons are like hyperactive children. If you give them room to move, they will take it. So let's imagine you have two electrons or two children running around this atom. Eventually, they're going to end up it's based on probability, they're going to end up on the same side of the atom at once. And that's going to create a temporary or fleeting or momentary or rapid dipole. And so that's going to induce a dipole in the neighboring atom, right? You have the delta negative here. That's going to create a delta positive that you see here. And then there's going to be an attraction between the two of them. However, eventually the electrons are going to go back to being evenly dispersed across the atom or molecule. And so again, London dispersion forces, they're fleeting, they're rapid, they're temporary, and they're very weak. They're the weakest of all the intermolecular forces. If I can just give you a word of encouragement as you move forward in this class or biology class or biochemistry or any other topic that has to do with chemistry or biology, if you understand intermolecular forces, meaning ion dipole interactions, hydrogen bonding, dipole dipole forces, and London forces, it will help you greatly. So, IMFs, intermolecular forces, the more you understand them, the easier or more straightforward chemistry can become. Now, something else that's interesting about intermolecular forces, like a London force, is that the shape and size of a molecule can affect attractive forces. Check this out. Remember how with the helium atom, I told you, well, there's two electrons and they're moving around rapidly, and probability states that they would be on one side of the atom in a moment of time, which creates a temporary dipole. Well, if you have a big molecule, this is N-pentane, which is, you can see it's got 5 carbons and 12 hydrogens. I'll just give you the formula here. It's C5H12. Anyhow, it's a long molecule. It's got a lot of electrons in it. But it says here the electron density clouds of large hydrocarbons, and a hydrocarbon is nothing more than a molecule that contains only carbon and hydrogen, so C and H. Um, the electron density clouds of large hydrocarbons are easily distorted. That means they're polarizable, meaning the electron cloud can be distorted. And so London dispersion forces increase with increasing molecule size. Additionally, so if the molecule gets bigger, it's going to have stronger London forces. Also, and this is kind of interesting, is that hydrocarbons that are shaped long and narrow tend to have stronger London forces than short globular molecules. So again, you notice that all three of these compounds, N-pentane, isopentane, and neopentane, they all have the same formula of C5H12. But what happens is that the boiling point and the melting points of these molecules decrease as you go from N-pentane to isopentane to neopentane. Why? Because when you have a molecule that's linear, like the N-pentane, it's going to have a strong attraction between two molecules of N-pentane. Because if I draw a second molecule that looks like this, maybe, okay, there's going to be a lot of surface area that can come into contact between the two molecules. But once you start branching it, like you see this branch sticking off here, you get less attraction. And so when you have one that's spherically shaped, excuse me, like this one here, where you can imagine between two spheres, you're going to have very little interaction between the molecules because only a small amount of two spheres can come into contact with each other. So the take-home message is when you have hydrocarbons, the London forces are going to increase with a bigger molecule, but if you're comparing molecules that are all the same size, like we are on here, the long and narrow ones are going to have stronger intermolecular forces than the short, more spherical. This is globular here, but the more short and spherically shaped molecules. All right, let's see if we can identify the strongest intermolecular force in each of these compounds. The first one is nitrogen triiodide. So if we draw a Lewis structure of nitrogen triiodide, and then we come up with a molecular geometry. Just let me try to make this a little prettier. It's going to look something like this. Okay. And so this molecule definitely has a dipole, right? Nitrogen is more electronegative than iodine, and so you're going to have a dipole going this way, this way, this way, and they won't cancel out. In fact, the net dipole is going to be going straight up like this. And so since this is a polar molecule, there's no hydrogen attached to the nitrogen. And so since this is a polar molecule, the strongest intermolecular force is going to be a dipole force. Okay. There's no ion. Okay. And of course it has London forces, but those aren't all that strong. The next one is HF, hydrogen fluoride. Right, we already saw this one, so you remember the HF. Fluorine is the most electronegative element in the periodic table, so it's going to be delta negative. The hydrogen is going to be delta plus. So if I have a neighboring HF molecule, right, you put the delta positive here, delta negative here, and there's going to be a hydrogen bond between the two, right, because we have the hydrogen bound to a fluorine. So we'll put here hydrogen bonding. And then in the last one, you have bromine. Well, bromine is just a diatomic molecule. And remember, there's no difference in electronegativity between two bromines. The difference in electronegativity will be zero. And so this is a nonpolar molecule. So there's no ion dipole, there's no hydrogen bonding, there's no dipole-dipole force, but there's going to be what? London forces, right? Everything has London forces, even nonpolar molecules. Okay, let's move on to section 5.4 and deal with energy and properties of matter. And first, let's start by defining kinetic and potential energy. So kinetic energy is the energy that a particle has as a result of motion. So kinetics, motion. So motion, okay. Then we have disruptive and cohesive forces. So disruptive forces are forces that result from particle motion, and they're associated with kinetic energy, whereas cohesive forces are the attractive forces between particles, like bonds, for example. They're associated with potential energy, and potential energy is energy that is stored in particles due to their position, composition, and arrangement. Right? Potential energy in a molecule, for example, is going to be stored in the bonds, right? If you eat a piece of meat, or maybe meat isn't a great example. Let's say you have a chocolate bar or something, right? It has sugar in it. Well, where does the energy come from? It comes from the bonds and the molecules of sucrose, right? That taste so good. So again, kinetic energy is the energy associated with motion. I should fill this in here. Potential energy is energy due to position. Okay. Then we have disruptive forces that are a result of particle motion. They're associated with kinetic energy. And then you have cohesive forces. They are associated with potential energy. Okay. All right. So example 5.5 says the acidity of our blood is maintained within a very narrow range by the bicarbonate buffering system. If you've ever studied pH before, the pH of blood, the pH of human blood, is somewhere between 7.35 and 7.45, somewhere in that ballpark. Is the energy stored in the ionic bond between the sodium cation and the bicarbonate ion in the sodium bicarbonate? Is that kinetic energy or potential energy? Well, remember, sodium is a cation and the bicarbonate ion is an anion. And so, since this is due to bonding, right, it doesn't have anything to do with motion, right? Um, this would be potential energy. Potential. I can spell potential energy. All right. Okay, physical properties and the states of matter. So physical properties that distinguish the state of matter. Some physical properties we're interested in this class are going to be density, as well as shape, compressibility, particle interaction, and molecule movement. And before we get into all of these, um, the states of matter, and look at all these different properties, let's take a look at this table 5.4. So you see the different properties here: density, shape, compressibility, particle interaction, molecule movement. Well, we see, first of all, that if we just start with shape, let's just start with shape. Okay. You see the solids have a definite shape, right? If you have a solid, let's imagine you have a marker or something. Well, a marker has a defined shape, right? You can't pour it or anything. Whereas a liquid, on the other hand, will take the shape of the whatever container you put it in. If you take water and pour it into any container, it's going to take on the shape of that container. Then a gas doesn't have any shape either. It's always going to take up the shape of its container, and it's going to fill it as well. Okay, so a gas will always fill whatever container you put it in. Well, let's take a look at the top. Okay, I should have covered this. Compressibility is the change in volume of a sample resulting from a pressure change acting on the sample. And you guys probably know that when it comes to compressibility, out of solid, liquid, and gases are definitely the most compressible. If you've ever played with a syringe or something, maybe, if you get children's Tylenol, I know my kids like to grab the syringe and fiddle around with it, and you can compress it, or even squeezing a tennis ball. You can compress the gas that's in there. Whereas liquids have a very low compressibility, which is a good thing because we could put liquid in our brake lines. And then finally, solids are virtually incompressible. And if we take a look at density, okay, the density of liquids and solids are going to be high, okay? Um, Solids and liquids, and I'm really stretching it here, but they're usually around 1.00 grams per milliliter or greater. So maybe I'll put greater than or equal to, and it can be less than too, but anyhow, maybe I should get that out of there. They're just going to be a lot higher than gases, okay? Gases have very low densities. Particle interaction in a solid, the particle interactions are going to be very strong, right? In a liquid, they're going to be intermediate, and then in a gas, they're going to be weak. And then finally, if we talk about molecular movement, okay, if you have a solid, well, obviously the molecules aren't moving a whole lot in the solid, right? But if you go to a liquid, well, in that case, the molecules are moving past one another when you pour it. And then in a gas, molecules just flow readily. So let's take a look at solids and liquids and gases in more detail. And this just kind of summarizes what we covered already. But if we look at solids, solids have high densities. You could take something like the density of gold is around 19 grams per centimeter cube. It's it's not the densest, but it's one of the densest substances known to man. Solids, again, they have definite shapes. Okay. They don't compress very well. They have strong particle interactions, and there's very little molecular movement. Liquids, on the other hand, it says their cohesive forces are slightly favored over disruptive forces. So that just means that liquids don't evaporate immediately. Okay, they're gonna, stay there and move around. So liquids have higher densities. They don't have a defined shape. They're always going to take on the shape of their container. Like I said, because of your brake lines, um, the reason brake lines use liquids is because they have a low compressibility, intermediate particle interactions, and substantial molecule movement. Gases, again, in gases, in liquids, cohesive forces are slightly favored over disruptive forces, but in gases, disruptive forces are going to be favored over cohesive. So maybe we should edit this in the slide here. I don't know why this is on here, but these are true. Gases have low densities. They don't have a defined shape. They're very compressible. The interaction between particles is extremely weak. In fact, sometimes we assume that don't interact with each other whatsoever, and there's a lot of molecular movement. And so this shouldn't be on here. This should be on the previous slide. So again, when you read the textbook, it'll tell you that gases, that disruptive forces are favored over cohesive forces. Okay, example 5.6, identify the state of matter of the substances printed in italics. So first one, the nitrous oxide administered to sedate a patient during dental procedures has a low density, so low density, and diffuses freely into the nasal hood. So nitrous oxide is a formula NO2. If it's got a low density and it flows freely, it must be a gas. Okay, and I'm sure you are well aware of that. The next one, ice chips. Okay. Ice chips have a definite shape. They have low compressibility, and are provided to individuals who are in the process of giving birth. Well, ice chips have a low compressibility and a definite shape. And so ice chips would be a solid.